Welcome back to Basic Electronics. In this lecture, we will look at the R2R ladder network and how it can be used to make up a DAC. We will then discuss analog to digital conversion. We will start with the flash ADC and then discuss other types of ADC. So let us start. Here is an example of the R2R ladder network, and this example corresponds to a 4-bit DAC. This node A0 corresponds to the LSB and this node A3 corresponds to the MSB. And note that we have only R or 2R in this network. We don't have any other resistance value. That is why it is called R2R ladder network. Okay, how does it work? Node AK is connected to VR, the reference voltage, if input bit SK is 1, else it is connected to ground. For example, if our LSB S0 is 1, then the voltage at this node will be VR, otherwise it will be 0. We can replace this original network for convenience in analysis with this equivalent network, and let us see why the two are the same. This node, the ground node here, is the same as this common node. Now let us consider this node here, which is A0, that one. The voltage at this A0 with respect to this node is S0 times VR. Now if S0 is 1, then the voltage at A0 is VR, otherwise it is 0. And that is exactly the functionality we had over here. And similarly, we connect a voltage supply S1 VR here, S2 VR here, S3 VR over here. Let us now find the Thevenin resistance of the R2R ladder network. And step number 1, we deactivate the independent sources, which we saw in the last slide. And after doing that, we get this network here. What we can do to begin with is to combine these two resistors. 2R parallel to R gives us R. So we get this circuit now. The rest of the circuit, of course, remains the same. Now we have R and R in series, and that in parallel with 2R. So that once again gives us R. And we can continue this process. These three can again be combined to give us R, like that. And finally, these three can be combined to give us R. So the Thevenin resistance, as seen from here, turns out to be R. Okay, so we have found the Thevenin resistance of the R2R ladder network. Next, let us find the Thevenin voltage corresponding to one specific bit equal to 1 with all others 0. If S0 is 1, then this voltage source is VR, and the voltage sources that we had over here are all 0. So that means there is a short circuit here. Okay, and now what we want to do is to find VTH as seen from this port. First, we can replace this part with its Thevenin equivalent. What is the Thevenin resistance? As seen from here, it is just 2R parallel to R, that is R. And what is the Thevenin voltage? The Thevenin voltage is the open circuit voltage here. So we remove all of that and find this voltage between this node and this node. And then we see that there is a voltage division happening between these two resistances. So this voltage will then be VR by 2. So that is what we get. The Thevenin resistance is R of this part, and the Thevenin voltage is VR by 2. Now we continue with this process. Note that this R and this R are in series. So this part looks exactly like this one, with only one difference, that is we have VR here, we now have VR by 2 over here. So then we will get this Thevenin equivalent R and VR by 4. Next, we can replace this network with its Thevenin equivalent, and we can anticipate that we're going to get RTH equal to R and VTH equal to half of this, that is VR by 8, like that. Once again, this network is exactly the same as any of these, except the voltage supply is now VR by 8. So we are going to get a Thevenin resistance RTH equal to R for this entire network, and a Thevenin voltage of half of this, that is VR by 16. So that is our final answer. So as seen from here, the Thevenin voltage is VR by 16. Next, let us consider S1 to be 1 and all other bits equal to 0. So we have VR here in the branch corresponding to S1 and 0 volts here, here and here. That means short circuit. Alright, once again we want to find the Thevenin voltage as seen from here. Let us start with this network. What is the Thevenin resistance? It is 2R parallel to R, which is R, that in series with R, so that is 2R. So that is what we get. And now we can replace this network with its Thevenin equivalent, and we have done that in the last slide. So we are going to get RTH equal to R and VTH equal to half of this voltage, like that. Okay, let us continue. We can now combine these components and get RTH equal to R again and VTH equal to half of this, that is VR by 4, like that. And then finally we combine these to get RTH equal to R and VTH equal to VR by 8. So that is our final answer. As seen from this port, VTH is VR by 8. Next, let us consider S2 equal to 1 and all other bits equal to 0. So the voltage supply is here now. To begin with, we can combine all these resistors. 2R parallel to R is R, R plus R is 2R, then 2R parallel to R again is R, and R plus R is 2R. So this entire network is equivalent to a single resistance 2R, like that. And now we can replace this network with RTH equal to R and VTH equal to VR by 2, like that. And finally, we can replace this network by RTH equal to R and VTH equal to half of this, that is VR by 4. So that is our VTH as seen from there. And finally, let us consider S3 equal to 1 and all other bits equal to 0. So we have the voltage source here now, VR, and these voltage sources are 0, so short circuits. Now this entire network can be replaced with a single resistance 2R, and you are encouraged to show that. So this is what we get. And now this network can be replaced with RTH equal to R and VTH equal to VR by 2, like that. So as seen from here, we have VTH equal to VR by 2. Okay, to summarize, our original network, this one, can be replaced with its Thevenin equivalent RTH and VTH, where RTH is R and VTH by superposition is the VTH arising from this source and VTH arising from this source, and so on. So then we get VTH due to S0 plus VTH due to S1, etc. And when we add all of these, we get VR by 16 times S0 2 raised to 0 plus S1 2 raised to 1 plus S2 2 raised to 2 plus S3 2 raised to 3. And we can now use this R2R ladder network and an op-amp circuit to make up a DAC, and we will see that in the next slide. So here is a DAC circuit made with an op-amp. This is our R2R ladder network, and as we have already seen, this entire network can be represented by its Thevenin equivalent RTH and VTH, and so now the circuit looks like this, and this is nothing but an inverting amplifier. So we have VO equal to minus RF by RTH times VTH, as simple as that. So we have VO equal to minus RF by RTH times VTH, and when we substitute for VTH from the last slide, we get this expression. Okay, and this can be extended to n bits, and we can then write for an n bit DAC, VO is minus RF by RTH times VTH, which is minus RF by RTH VR by 2 raised to n summation 0 to n minus 1 Sk 2 raised to k. Like we said earlier, electronics is full of clever things, and the R2R ladder network is definitely one of them. Okay, now these DACs based on the R2R ladder network are commercially available, ranging from 6-bit DACs to 20-bit DACs, and they are available as a single package, that is in monolithic form, single chip, and they can be made using the bipolar technology or the CMOS technology, or a combination of the two, which is BiCMOS technology. And needless to say, higher the number of bits, more expensive is the IC. Here is some homework for you. In this circuit, we have a combination of weighted resistor and R2R ladder networks. So here is our weighted resistor array, R2R, 4R, 8R, also here R2R, 4R, 8R. And you need to find the value of R, this small r here, for the circuit to work as a regular DAC, that is binary to analog. That would be an 8-bit DAC. This is the LSB S0, and that is the MSB. That is part 1. Part 2, find the value of small r for the circuit to work as a BCD to analog DAC. There is a very important specification of a practical DAC, and that is the settling time. Let us take a 4-bit DAC as an example, and let us say we are changing our binary input number from say 0011 to 1100. As a result of that, our analog output is going to change. This is our initial value, and that is our final value, and it's going to take some time for this initial value to change to the final value. So when there is a change in the input binary number, the output VA takes a finite time to settle to the new value. This finite settling time arises because of stray capacitances and switching delays of the semiconductor devices used within the DAC chip. And manufacturers will of course strive to make this settling time as small as possible, but it cannot be made 0. Okay. Now this is how the settling time is specified in a data sheet. For example, 500 nanoseconds to 0.2% of full scale. Let us see what this means. Let's say our initial value corresponding to our initial binary number is 1 volt, and the final value corresponding to the new binary number is 2 volts. So our VA has to change from 1 volt to 2 volts. Suppose our full scale is 10 volts and 0.2% of 10 volts is 20 millivolts. So that means to go from 1 volt to within 20 millivolts of 2 volts is going to take 500 nanoseconds. So that is what this specification means. We will now discuss analog to digital conversion, and let's take this example. of a 3-bit ADC, analog to digital converter. Here is the analog input, which we will denote by VA, and this is the digital output. Since it's a 3-bit ADC, we have 3 bits here, D2, D1, D0. This is the MSB and that is the LSB. Apart from that, this ADC has 2 additional pins, ground and a reference voltage. Here is a schematic diagram showing what an ADC should do. In this case, we have a 3-bit ADC. So this interval between 0 and Vmax, which is the same as VR, is divided into 8 intervals, that is 2 raised to 3, and these intervals are labeled 000, 001, 010, etc. all the way up to 111. Now the given input voltage VA prime is compared with each of these levels, 0, VR1, VR2, VR3, etc. and if it falls between these two levels, for example, then the output of 100 is assigned. So this is the MSB, so D2 would be 1, D1 would be 0 and D0 would be 0. Here is the summary. If the input VA is in the range VRK to VRK plus 1, the output is the binary number corresponding to that integer k, this one. For example, for VA equal to VA prime, this VA prime, it fell between VR4 and VR5, and therefore the binary number corresponding to 4, which is 100, is assigned to the digital output. We may think of each voltage interval corresponding to 000, 001, etc., these intervals, as a bin or a box. In the above example, the input voltage VA prime falls in the 100 bin, this bin here, and therefore the output of the ADC would be 100. And finally, note that for an n-bit ADC, there would be 2 raised to n bins. In this case, there are 2 raised to 3 or 8 bins. So the basic idea behind an ADC is quite simple. First, we generate reference voltages VR1, VR2, etc., these levels. Then we compare the input VA with each of these reference voltages to figure out which bin it belongs to. And if VA belongs to bin K, then we convert K to the binary format, and that is our ADC output. And a parallel ADC does exactly that, and let us see that in the next slide. Here is a schematic diagram of a 3-bit parallel or flash ADC, and let us see how it works. Let us look at this figure. We need to generate VR1, VR2 up to VR7, that is 7 reference voltages, and that is done by this resistor network over here. For example, VR1 would be R by 2 divided by this total resistance multiplied by VR. What is the total resistance? We have R by 2 here, then we have 6 of these R's, so that means 6R, and another R by 2, so that is 7R in all. So VR1 would be R by 2 divided by 7R times VR. VR2 would be 3R by 2 divided by 7R times VR, and so on. Next, we have these comparators. One input for all comparators is common, that is the plus input, and that is connected to the applied analog voltage VA. The second input, the minus input, is VR1 for this comparator, it is VR2 for this comparator, and so on. Now let us take an example. Let us say that VA is this VA prime, which falls between VR4 and VR5. So the output of this comparator, which is denoted by C3, is going to be 1 in this case, because VA is greater than VR4. C2 also is going to be 1 because VA is also greater than VR3, and C1, C0 are also going to be 1. On the other hand, C4 is going to be 0 because VA is less than VR5, and also C5 and C6 are going to be 0. So we have 0, 0, 0, 1, 1, 1, 1, and now we have this logic which can figure out what combination this situation should correspond to, and the output of this logic is D2, D1, D0. That is our ADC output. So that is how this parallel or flash ADC works. So this circuit, which we saw in the last slide, represents a 3-bit parallel ADC, but there is a practical difficulty with this circuit, and that is, as the input changes, the comparator outputs C0, C1, etc., these outputs may not settle to their new values at the same time. This might settle earlier, this might settle later, and so on. And therefore, the ADC output will depend on when we actually sample D2, D1, D0, and that is not desirable. And to circumvent that difficulty, what we do is add D flip-flops as shown over here. Allow sufficient time between the change in VA and the active clock edge so that the comparator outputs have already settled to their new values before they get latched in. So what does it mean? Let us take an example. Let us say this comparator takes 50 nanoseconds to settle down. That means when we change VA from VA1 to VA2, from that time it takes 50 nanoseconds or less for all of these outputs to settle down. In that case, we can make sure that our active clock edge here is 50 nanoseconds after the analog voltage has changed, and then we are sure that these values Q0, Q1, Q2, etc. are consistent with the new analog voltage VA2, and then we get the correct D2, D1, D0 at the output. Let us make a few remarks about the parallel or flash ADC. In the parallel ADC, the conversion gets done in parallel since all comparators operate on the same input voltage. That we have already seen. All of these comparators get the same input voltage as V+. Conversion time is governed only by the comparator response time, and that makes the conversion very fast. Hence the name flash converter. The conversion happens in a flash. That is why the name flash converter. Flash ADCs to handle 500 million analog samples per second are commercially available. So that is how fast these flash ADCs can get. What is the disadvantage? We need 2n comparators, strictly speaking 2n-1, for an n-bit ADC. Here we have n equal to 3 and we require 7 comparators, which is 2^3-1. So as n grows, this number becomes very large, impractically large, and therefore these parallel or flash ADCs are generally limited to 8 bits. To summarize, we have looked at the R2R ladder network and its advantage over the weighted binary register array. We have seen how a DAC can be constructed using the R2R ladder network. We then started our discussion of analog to digital conversion. After looking at the basic idea of A to D conversion, we looked at one implementation, namely the flash ADC. The flash ADC is fast, but it requires a large number of comparators when the number of bits is increased. In the next lecture, we will look at other ADC types which offer a large number of bits, that is a higher resolution at the expense of speed. So see you in next class.